revisit the fundamentals of working stress design. We did consider this type of beam cross section. We defined the distance from the neutral axis to the extreme concrete compression fiber as KT. And then at the stress diagram, we are dealing with linearly distributed form of stresses defined as Fc prime and denoted as Fe or Fs over n. And this stress can be considered as forces in two distinct directions but equal in magnitude, C and T respectively, as compressive and tensile forces, defined by separating moment arm JD from KD over 3 at the extreme compression concrete fiber. In essence, we are dealing with internal couple for CJD and TJD as M. This working stress design can be called as well as elastic design since we are dealing with elastic limit situation. And we can also set this up to call it as allowable stress design since we are dealing with such type of allowable, dealing with concrete and of reinforcing steel. Stress design method, which we did consider section after bending. Second, Hooke's law, that stress is proportional to strain, applies to both the steel and the concrete. And then third, the tensile strength of concrete out from the analysis and until such time we reach the design stage. And then also the bond strength between the concrete and the steel is perfect, so no slip occurs. So with the aid of this fundamental insights in the working stress design, we did dwell ourselves in analyzing singly reinforced, doubly reinforced, or reinforced for tension and reinforced for tension and compression. We take into consideration as well the pre-stress concrete. We also consider some of the analysis that requires principles from the WSD. Now, we are going to deal with the fundamentals of ultimate strength design. This ultimate strength design can be called as well as strength design. So the assumptions for the USD method is that number one, plane section before bending remains plane section after bending. The stresses and strain are approximately proportional only up to moderate loads. The tensile strength of the concrete is neglected. The maximum usable concrete compressive strain at the extreme fiber is assumed equal to 0.003. The steel is assumed to be uniformly strained to the strain that exists at the level of the centroid of the steel. The bond between the steel and concrete is perfect and no slip occurs. And if we are going to look into the model section of this USD, so we have this as the neutral axis, the main reinforcing bars. So the strain diagram is presented this one accordingly as indicated in the assumption that the maximum usable compressive strain would be for concrete is 0.003. And this must be depicted as the strain of the steel. The strain of the steel must be greater than equal to the yield strain of this steel. So if in working stress design, we dwell on a linear stress presented diagram. Here, we are prompted with this type of diagram as a stress diagram. And this transverse dimension here is the compressive strength of concrete. While this one is Fs or the yield stress or Fy of the reinforcing bar as a limit. You take notice that this is not constant all throughout. This is somewhat parabolic in sense. So this Fc prime can be analyzed this way, but it will be hard enough to consider the actual strength of this concrete stress. So this resultant represented as N sub C and this force here represented as N sub T creates an internal couple which can be depicted or anchored the same concept with the WSE. It's just that this will play vital role in the subsequent slides. This see here. So let us continue this one. So we have this type of actual compressive stress block, which will be hard enough to analyze because of geometric configuration. The majority of the prime movers of the structural engineering industry made a concept, particularly in order to analyze this type of configuration. But in this case, the assumed compressive stress block will now be presented as rectangular equivalent compressive stress block. And instead of full Fc prime here, it will be about 85% of that full strength in concrete. And this height, C, will now be in a particular value, but not equal to C, but this will be a height A, generally presented or denoted as A, must be equal to the product of beta 1 and a C. And this is still Fy, and this MC then can now be analyzed as the extent of the resultant of this rectangular equivalent compressive stress block. And that is equal to 0.85 Fc prime times A times the transverse width, which is B. So in turn, we also have N sub T here, but that is the representation of the AS and the Fy, and that constitutes N sub T. This internal couple NC and Z, which is represented as the difference of D and A over 2, and NT and Z, which is also an internal couple, which these two couples are equal. This is the equivalent stress block for strength design and analysis. So as we can glean in the equivalent stress block for strength design and analysis in perspective, so this is the transverse section, this is 0.85 Fc prime, this is the A, and the C is defined as the distance from the neutral axis to the extreme concrete compressive fiber or compression fiber. This NC here is reflected at the center of gravity of this rectangular stress block, actually parallelified in sense, but rectangular in this side view. And this is the AS in dealing with the representation of the model section as NT here, that is AS that one. This A, defined as the product of beta 1 and C, is actually the height or the altitude of the equivalent rectangular stress block, compressive rectangular stress block. In this C, as I have uttered, this is the distance from the outer compressive fiber to the neutral axis, while beta sub 1 is a factor that is a function of the strength of the concrete. This beta sub 1 plays important role in dealing with whether analysis or design, which is a factor taken from 2,500 to 4,000 psi Fc prime equal to 0.85 as constant. If the magnitude of the Fc prime goes beyond 4,000, it will be less than 0.85. Until such time it reaches 8,000 psi for the compressive strength, the beta sub 1 then will be equal to 0.65. So in English natural unit, for Fc prime greater than equal to 2,500 PSI but less than equal to 4,000 PSI, as I have uttered here, that will be 0.85. For those values of FC prime greater than 4,000 PSI, this will be the consideration for beta sub 1, which can be derived coming from this one. And this is 0.85 minus 0.05 FC prime minus 4,000 all over 1,000. That's nearly a conversion greater than equal to 0.65. So in SI units, if you are dealing with FC prime greater than equal to 17 but less than equal to 28 megapascal, beta sub 1 is 0.85. If this ranges from 28 to 55 megapascal, this will be the beta sub 1. 0.85 minus 0.05 times FC prime minus 28 over 7. And if the magnitude of FC prime is greater than equal to 55, beta sub 1 is 0.65. We are asked to determine the nominal moment for the beam of cross-section shown using the material strength FC prime 27.6 megapascal and Fy 414 megapascal for the first articulation. Well, initially, we have this one. Uh, 250 to 575 as the model section. Wait na. Then we have this as the strain diagram, and this will be C, 0.85 C, that's beta, because we are dealing with 27.6 megapascal. This will be 0.85 FC prime, this is the resultant, this is MPAS at point. We are asked to find the nominal moment. So we start with the stress block. We equate that. So by virtue of this simple equation, we can compute for the A. And this is equal to 104.61 millimeters. And then we compute for the length of the lever arm, which is equal to D minus A over 2, which can be computed because of the given effective depth. And that is equal to 522.7 millimeters. Then we compute the nominal moment. This will be equal to NCZ, which is equal to 320.7 kilonewton meter. If you're going to calculate this one, and then by virtue of this one, and we have 320.7 kilonewton. You calculate this one. This is the nominal moment for that matter. Then we check the strain. So for the strain, we have the following consideration. 0.03 for that extent. So 8 is equal to beta 1C. We know that already. Because of this magnitude, beta sub 1 is 0.85. C then can be calculated as 123. 0.07 millimeters. And then by similar triangles, we have this 0.03 is to C. Epsilon sub T is to D minus C. That's the effective depth minus the C. And we can then solve for the yield, the strain for this steel. Define as 0.011 millimeter per millimeter. Actually, that's dimensionless or unitless. And then we can deal with the strain, Fy over ES, that's the yield strain. So what's the indication of this strain? This is apparently greater than this one. So because the computed strain in the steel 0.011 is greater than this strain, the steel reaches its yield stress before the concrete reaches its strain of 0.003. And the assumption that the stress is still is equal to the yield stress was correct. So that's articulation number one. The strain distribution of failure modes in flexural members. So if we are dealing with this type of strain magnitude, for example, you did compute the strain for the steel and it deals with this type of the balance neutral axis, then we are dealing at a sense of ductile failure. Yung parang if you look into the burning rubber, parang kumukuluntoy, parang gano'n, yung failure ng bakal. But if you will be dealing with this type of magnitude of strain, wherein the neutral axis is below the balance neutral axis, then the failure will be in the sense of brittle, yung parang malutong, yung yung failure niya. So, in the strain limit definitions, we have the following compartments: compression control, the compression control, the strain will be from 0 to 0.02. So that will be brittle failure. If the strain, that would be tension control. The transition region entails the following magnitude or range for the strain. Also, this will be the moment reduction factor, wherein the strength moment reduction factor for tension control will be 0.9. So for tension control, which is actually ductile failure, that phi as strength reduction factor is equal to 0.9. If we are in transition region, that would be 0.65 to 0.9. And if we are in compression control, the moment reduction factor would be 0.65. We are asked to determine the amount of steel AS required to cause the strain in the tension steel to be 0.05, just as the maximum strain in the concrete reaches 0.03. Megapascal for the steel. This is articulation number 2. We do the same projection of the diagram, the model section, and then the strain. So what we are going to deal with is the magnitude of this strain, that's 0.05, and this is equal to the C as defined from the neutral axis to the extreme concrete compression fiber. This is the difference of the effective depth and the C. And this will be A, that's about beta 1 times C, 0.85 FC prime, NCNT, and you know this already, as C, D minus A over 2. So we locate the neutral axis. So in locating the neutral axis, by virtue of what is given, that would be C is to 0, by similar, C is to 0.003, and this one as to this altitude. And then we can compute for C. Well, we know this already, that beta 1 is given as 0.85 accordingly. 8 can be computed. Already have the A, we can then compute for NC. And this NC is equal, that's NC is 0.85 FC prime AB, and is equal to 886.9 kilonewtons. And we determine the AS. The AS is equal to NT, which is equal to AS FY, which is equal to that magnitude. And that AS, based on the given FY, is equal to 2,142.2 square millimeters. For the epsilon to or computed this way, just as the maximum concrete strain reaches as well, then by virtue of this magnitude na 0.03, the AS is equal to this. This is the maximum amount of steel for the section to be tension controlled. Any steel in excess of this one cause to be less than 0.05. It will no longer be tension controlled. It might be on transition region or compression control. So this is the threshold for steel reinforcement. So let's say we are going to double the steel reinforcement by virtue of its magnitude and recalculate the nominal moment for the beam of the same cross section with the same material strength. So as articulation number 3. In here, we have this set up. So this will be presented as we double the magnitude of AS based on the given AS a while ago. This one. This will be double. And by considering that double in magnitude, well, as an assumption, the strength or the nominal moment will then be magnified to that percent. But let's see. If we double the AS, we capitalize on enhancing the magnitude of the nominal moment. But as an assumption, since we increase this by 100%, it can be increased to a maximum of 100% as well. But let us check that. ASFY over 0.85 FC prime B is nearly the equal magnitude of MC and MT. And A can be computed based on this one, which is equal to 209.22 millimeters, which can be then utilized to compute the nominal moment. And this nominal moment is equal to 577.21 kilonewton meter. If you will remember, the nominal moment a while ago is equal to 320.7 kilonewton meter. Is a bit higher to that one, but the extent of its dominant value simply 80%. That's the difference of this divided by 320. So 80% increase. 100% increase in a steel reinforcement will not guarantee
Iwan ko na yung paperboard dun.
Bakit?
Wala akong paglalay, magdumay na sa atin yan.
Atras mo muna.
Recording in progress to the required strength. Apparently, because that serves in WSD as the allowable. So that is set as furnace strength. And we will be dealing with factors. These factors are safety factors. So at first, the U, which is an indicative that this one is ultimate load. The ultimate load is the sum of the product of 1.2 for the dead load, 1.6 for the live load as a factor. And this must be greater than equal to 1.4 of the dead load as a greater check of the ultimate load. Where practical moment strength will be the, if you will remember, the strength reduction factor we discussed in the compression control, transition region, and tension control. 0.9 for tension control. So 0.65 to 0.9 for the transition region and 0.65 for compression control. Since we will be dealing with dominant strength of the steel in tension, this will be 0.9. So the ACI code, section 9.8 provides for this variable by using following C factors for tension controls, 0.9, 0.75 for compression control, section but spirally reinforced. Other reinforced member would be 0.65. And shear and torsion would be 0.75, bearing on concrete, which is then considered
Ito yung pinaka-authentic.
the computation of the T. That would be 0.65 plus 0.9 minus 0.65, 0.059 as epsilon y, the difference of epsilon T and epsilon y. Or this is valid for the range of epsilon T greater than equal to the yield strain, but less than equal to the 0.005, which is the threshold for the tension control. Assuming the yield strain is 0.002, this expression becomes this one. So, and it can then be presented as this one by virtue of the formula for C. And can be simplified further as this one minus this one. Not minus, multiply by that one. Minus. So, this AS minimum, if this is in English, this will be in SI. 0.25 square root of FC prime over Fy, transverse section B and D as effective depth must be greater than equal to 1.4 PD over F1. For the design criteria, the required Sn is less than equal to lowercase u. For phi, the modification factor or safety factor, multiplied by Sn must be greater than equal to u. So the u here is the calculated internal forces at critical section due to ultimate. The reduction factor is
Wala. Hindi, huwag mo na patayin. Wala kang signal. Pinatay mo pala eh.
to the PMN. It can be translated as well to the shear, to the torsion, to the force. And for the load combination, there are factored load combinations to be considered, but allow me to refresh your minds about the NSCP last 2001 and 2010. These are the types of load combination, wherein the load due to fluids is the F, H is the load due to lateral pressure of soil and water in soil, P is the notation for self-straining force and effects arising from contraction or expansion resulting from temperature change, shrinkage, moisture change, creep in component materials, movement due to different settlement or combinations thereof. And then F1 here, presented in this case in NSCP 2010, is 1.0 for floors and faces of public assembly, for live load in excess of 4.8 kilopascal, and for garage live load of 0.5 for all equals 0.5 for other live loads. Now, the NSCP in 2015, this will be the governing factored load combinations. So 1.4D, 1.2D plus 1.6 plus 0.5 of the live load and the rain load. And then 1.2D, 1.6 live load, rain load. And this one is the wind load. This will be the combination if you will be dealing with dead load, wind load, live load, and the LR is simply the reduction for that matter. And then live load and the earthquake load. And then wind load and then earthquake load. So as we can glean in the design assumption of the model diagram or model section, for the equivalent rectangular stress block, so we have this in singly reinforced rectangular beam. This is the AS. This is the A. This is A over 2, and this is the D effective depth. Well, naturally, you know this already. From the neutral axis to the extreme compression concrete fiber, that is the C. And A is equal to beta 1 times C. Initially, we have this type of stress distribution, which is hard to consider or analyze. So that's why we did present this, not me, not us, but those prime movers of the structural engineering concepts
Nakita yung labas eh.
in this rectangular equivalent
Baka
stress
yung
block.
kailangan ni ano, yung backlight.
Oo.
Baka lumayan.
And we can also employ this in rectangular shape, just like this one. But this must be presented accordingly based on its extent of neutral axis and the center of gravity of this triangular area. This will still be A, but this must be C accordingly. So this is the stress distribution, and this will be the rectangular setup. So please take note. This is A over 2, this is 2/3 because of the extent of representation of the area.
Parang muntihan na to.
For the sectional strength, A is equal to C beta 1. We already know this one. And by equilibrium, that will be 0.85 FC5 AD. Well, it can be represented as NC or merely uppercase C. NP or merely uppercase C as ASFS for non-yielding, ASFY for yielding, as the notations dictate. So by taking moment as equilibrium, that will be 0.85 FC5 AB times D minus A over 2. And we can also check that by utilizing the T as one of the internal couple. For the steel tensile stress condition, we have case 1, non-yielding condition. Concrete crashes at strain 0.003. And then the stress of the steel will be less than the yield stress. Then Fs is equal to Es and epsilon S. By strain compatibility, so we have this strain diagram. You know this already, and this will be presented this way. This will be set up to this one if we're going to come up with Fs employing Es or plugging Es as 200,000 megapascal. So by virtue of similar triangle, we already have this. And by capitalizing on the extent of this given constant and this as epsilon S, we can then arrive 600 D minus C over C for Fs. This is the theoretical tensile stress when concrete crashes. So for the yielding condition, that's Fs greater than equal to Fy. The T then will be equal to As Fy. That's the yield stress. And then we are going to use Fs equals Fy for Fs is independent to strain. So the conditions of failure entails the following. It depends on strain conditions of concrete and steel. So compression controlled failure.
Ay, lamig ko nito.
So that implies concrete crashes before steel yields. Abrupt collapse of membrane. And the strain of the steel is less than the yield strain. And that will be Fy over Es. For the for rectangular stirrups,
Hindi yung
we're going to use 0.65. For spiral stirrups or ties, we're going to use 0.75. For tension controlled failure, steel is way beyond yielding before concrete crashes. Gradual collapse due to yielding phase. So epsilon is greater than equal to 0.005. That's the tension control failure. And the phi here is 0.9, or the reduction factor is 0.9. For the transition failure,
Ang dilim na ilaw.
still just yielded, and this will be less than 0.05, but greater than the yield strain. And this will be the formula for it. This one has been presented a while ago. But this will be a phi ranging from 0.65 to 0.9 by virtue of interpolation. And this has been presented a while ago according to the strain limits, compression controlled, tension controlled, and transition region. The reinforcement of strain is greater than equal to 0.04. Always maintain tension controlled design. So we do not want to yield our design in this number 1 and in number 2. I mean number 3. And then the reinforcement limits, this has been presented in English units, I mean in SI units, 0.25 FC prime over Fy BD, and then 1.4 BD over Fy, whichever is larger. And then for the alternate equation of singly reinforced rectangular beam, we have this particular one, phi, the reduction factor P and the Mn. This P is 0.9. And then this is, you know this already, 0.85 FC prime ABD minus D over 2. And this can be represented as this one if we will be dealing with rho as AS over BD. This is the still ratio, this is Fy, and this will entail a representation of it. So phi rho Fy BD squared minus times 1 minus rho Fy over 1.7 FC prime. Or we can then represent this as this one as 1 minus 0.59 rho Fy over FC prime. Where the depth of stress block is still A, generally an important variable, we solve from C is equal to T. We always do that. And C is equal to NT, or C is equal to T. For us to solve the A, and then we can then solve for the C if we know already the A. And then the balance strain condition. So as we explained a while ago about this particular setup for the balance strain. So this is the balance that depicts the neutral axis imbalance. So this is ductile failure because of the extent of the neutral axis located somewhere above the balance neutral axis. And this one will be below, this one will be a brittle failure. And this is in essence a representation of the balance and tension control. This is 600D by virtue of similar triangles, and then 0.85 FC prime for the balance. As we take a look at this formula, 0.85 FC prime beta 1 over Fy times 600 over 600% point. Tension control condition. This will be the setup. The C at 5, 0.005 will be 3 over 8D. This will be the setup for that matter. 0.85 FC prime beta 1 over M3 over 8. General equation for the relationship is this one. For the strain, which is
Ba't nawala? Pwede ba? Kailangan ko na lang ito eh. Ako na.
Siya ata nawala mali.
Recording in progress.
We have the minimum tensile steel ratio that is depicted as 0.25 square root of FC prime over Fy, or 1.4 over Fy. For the limiting strain, we have 0.04 greater than or equal to the strain of the steel. That will be 0.04 as the threshold. And for the maximum, will be 0.85 FC prime beta 1 over Fy times 3 over 7. This rho will be utilized in computation of the steel reinforcement. That's rho BD equals AS equals ES. So, if the computed rho is less than the minimum steel ratio, then we will use the steel ratio in minimum. If the computed steel ratio is greater than the maximum steel ratio, then we are going to revisit our design and design dimension and or analyze it as doubly reinforced. So, ganun lang. Kapag bumaba sa minimum, gamitin yung minimum. Pag tumaas sa maximum, hindi mo gagamitin yung maximum. Kasi ang kailangan mo yung value na to eh. Ibig sabihin may sobra. Parang sa WSD may excess. Yung excess na yun yung gagamitin para magkaroon ka ng doubly reinforced. Para magkaroon na ng kaparaanan yung mandatory force na magbubukat din siya. Lagay lang natin sa perspective yung tension control, transition control, at saka compression control. Dinaliktad ko lang yan. Nandito yung kanina. So this is 0.9. This is 0.65. Alam niya na, ito yung range. 0.9 to 0.65. I mean 0.65 to 0.9. So this will be the minimum, the balance, and the maximum. Okay, pag ang kinumpute mo, siyempre we open align our design in the tension control kasi hindi abrupt yung collapse dito. So pag ang sinasabi lang dito, kapag na-compute mong steel ratio ay mababa pa rito, gamitin mo ito na yung pinakamababa. Pero ang na-compute mo mataas na steel ratio dahil napansin mo upon verifying it, mas mataas pa sa maximum. Yung sobra na yun, gagamitin mo para ma-design yung dimension o kapag hindi pa rin nakuha yung recomputed steel ratio, mag-double reinforce ka na. So design for positive and negative moment. Well, apparently you know this already from the working stress design principles. So kapag nandito yung positive, ano ba nagmamanifest ang positive moment? Di ba? Naalala nyo, di ba? That indicates concave upward. Ibig sabihin, the main bars must be placed at the bottom. The main bars. If you are dealing with doubly reinforced, the tension bars will be at the bottom. The compression bars will be at the top. If you are dealing with negative moments, that indicates concave downward. So the concavity of the elastic curve simply dictates that the position of the main bars will be placed at the top while the mandatory bars will be at the bottom. If you are dealing with a doubly reinforced, the tension bars will be at the top for the negative moment and the compression bars will be at the bottom. This are merely reminder. For the doubly reinforced rectangular beams, so we set the limiting strain. We know the maximum. Sumobra. Kinumpute mo yung steel ratio, sumobra sa maximum. Doubly reinforced tayo. So, punta tayo dito. Sumobra eh. So, pag may doubly reinforced, nandito ka na sa maximum. Within the transition control. So, if this will be less than the strain of 0.004, then we do consider a doubly reinforced. Or the second checking is that the steel ratio is greater than the maximum steel ratio. So for the doubly reinforced rectangular beams, do not get overwhelmed with this one. Allow me to set things first in clear perspective. So this will be tension bars. This will be compression bars. This normally set as AS. This naturally set as AS prime. This will be P. This will be C sub C for the compression bars. And this will be, I mean, C prime for the compression bars. The C sub C here is good for the concrete. We will be dealing with the same strain diagram. It's just a matter of presenting it as epsilon. And this will be the maximum strain for concrete. That is the threshold, 0.03. So this will be half of A. This will still be C. We know this already that this is A. And A is beta 1 times C. And that's the essence of if we call it balance moment in the working stress system. So by virtue of that idea, so we know already that this will be the maximum AS. We add to the yielding effect of the compression bars and the additional tension bars needed in the excess moment. So this will be D prime, this will be D minus D prime. Usually accounted as 60 millimeters or 65 millimeters. So that extends the idea of dealing with the summation of concrete cover, diameter of the stirrups, and half of the diameter of the nipples. So we know this as the summation of PMN. That will be PMN1 plus PMN2. And this will be AS1, which is the maximum, and plus AS2 as the total AS. And then we know this as T, T1, T2, AS1 FS, AS2 FS. The yielding setup is FY. So the C sub C for the concrete, that's 0.85 FC prime AB, AS prime for FS double prime. By strain compatibility, we have this one, by similar triangle. And then by virtue of the magnitude of the E as modulus elasticity, we can then derive this formula, 600 times D minus C over C. Is my audio clear?
Yes, bro. Yes.
Okay. Thank you. Nagpapapper. Sandali lang Puminto siya. Ayaw Siguro kailangan lang kumain ako. Ayaw pa rin. Gutom na ako eh. Ayaw pa rin.
Magsalita ng matagal. Magsalita.
Teka lang Anong mangyari?
Batak na. Maubos yung ano.
Come on, baby.
Bigat na.
Let's do the locomotion. Anyone? Nandiyan pa ba kayo?
Yes, sir.
Good.
Yes.
Wait lang Kape, gusto niyo kape? Hintay muna kayo sa saglit. Ano magyari dito ba? Uy. Yun. Bako nga to. Yun. Ano na ba nangyari?
Kailangan talaga ng kape na sir.
Kailangan talaga ng kape, no? Wala eh. Teka lang Okay. Labo. Kasama ka naman. Paano nga mo na? Malakas ba ulan sa inyo? Malakas ang ulan sa amin.
Opo, sir. Yes, sir. Wala to.
Baya. Malapit na eh. Ito na eh. Wala pa. Wala na siya. Segundo lang, tol. Balik tayo sa link. Thank you.
I-end yung session mo. Sama ka na.
Wala pa naman pag nawala na.
Sabi niya.
Basta leave mo.
Balik lang doon sa link.
Leave mo.
Tapos lunch meeting ulit.
Hindi, back mo muna. Shot mo na sa gilid.
Ito.
Yan.
Recording in progress.
Sa gilid.
It happens. Wala.
Recording stopped.
Pwede ka na siguro na hindi maligo. Palit ka na lang ng damit.
Naman naman ikaw gagawin yung gano'n.
Maliligo. Baba. Baba ka rin pala.
Recording in progress.
Bagal pa.
Hindi ko nga pare. Akala ko nakatingin lang.
Sayang. Ano ba tayo? So we did consider the strain compatibility. This is epsilon s fs prime es, and this will be that's epsilon s prime. No, mali lang yung pagkakasulat. And this is 0.003 c minus d prime over c. And then by virtue of this magnitude, fs prime will be 600 times c minus d prime over c. For doubly reinforced rectangular beams, we do have this one. So we set the mu1 as Tmn1, and then we're in mn1 is T1d minus a over 2. That is equal to the concrete magnitude. That's multiplied by d minus a over 2. By virtue of equilibrium, we have c sub c equated to p sub 1, which is set as this formula, 0.85 fc prime ab as1 fs. And then we set mu2 as equated to Tmn1, and this will be equated to the yielding point or setup of CS prime and T2, and this will be multiplied by both magnitude of d minus d prime, and then we equate CS prime and T2 based on this yielding setup. And then AS prime, FS prime for the compression members will be equated to AS2 FS. Then from there, we know this already, AS is equal to AS1 plus AS2. Then we proceed with the design proper. So, for the three types of reinforced concrete beams, we have balance section, reinforced concrete beam section in which tension steel also reaches yield strain simultaneously as the concrete reaches the failure strain in bending. But actually, we did consider this one as the balance section. So okay yan, na ginagamit natin sa design. Yung over-reinforced concrete beam sections in which the failure strain in concrete reached earlier than the yield strain of steel. Hindi maganda to. So ito yung biglang babagsak. So akala ng laymanized term para sa non-technical person, ang over-reinforced ay para mas tumibay. Di ba naalala ninyo kanina na pag dinamihan mo yung bakal, hindi naman tumibay. 80% lang. Ibig sabihin hindi siya sumasabay sa paglaki mo ng dami ng bakal. So pag dinamihan mo ng bakal, bababa ng bababa ang moment. So hindi siya nagtatranslate sa paglakas ng section. Nag-create siya ng sitwasyon na maaaring ikabagsak ng structural element na yun. Kaya we do not allow over-reinforced. Dapat under-reinforced. Reinforced concrete beam sections in which the steel reaches yield strain at loads lower than the load at which the concrete reaches failure strain. For the rectangular beam analysis for tension reinforcement, reminder lang doon sa process, sa algorithm natin, algorithm, so that will be 0.85 mm, nominal moment. Alam na natin yan. Yan yung steel ratio. Yan yung kukompute na alala nyo sa steel ratio analysis natin. So this will be that one. So yung A, makikita mo na kapag ginamitan mo to, ito yung lalabas. Yun lang yung nangyari doon. Kaya nagkaroon ka ng formula. Maya-maya, mag-present natin. This is set as omega. When this, by virtue of the formula for that sense, for beta and C, So you will have that A. And PMN, so kung ano yung nandito, palitan mo lang. Ito yun. Then you simplify it. So by virtue of simplifying, you will arrive at a coefficient. We call this as coefficient of resistance. So FC prime omega times 1 minus 0.59 omega, where omega is the product of the still ratio and the ratio of the strength, the yield strength and the compressive strength of steel. Ano ba ito? Palipat ako rito. And then, by virtue of that coefficient, naalala niyo ba yung moment coefficient resistance na R sa WSD? R, di ba, ang R ay 1/2 FC kJ, na kung saan ang FC ay 0.45 FC plus kJ. Yung R na yun, parang KR yun. K-bar. The distinction between USD and the WSD, you have a safety factor. So, hindi buo yung kinoconsider natin sa USD. So, 90% lang, contention control. So, meron kang buffer. So, kung kumalas ito sa 90%, safe ka pa rin. Kasi meron ka pang 10% na kakarga dun sa sobra na yon. Pag talaga hindi na kaya, magdo-double reverse ka. So, by virtue of similar triangle, this will be the formula. This will still be the A and the beta sub 1 and the formula for A. And this will then be arrived and or derived by this working relation. And it can be further simplified as this one. 0.00255 FC prime beta 1 over rho Fy minus 0.003. Okay, let's have this one as articulation number 4. We are asked to determine if 6 meter long is 3 by 300 millimeter by 500 millimeter beam dimension with 4 number 8 bar is adequate to support the service loads. The uniformly distributed load is 9.5 kilonewton per linear meter. Live load is 11.7 kilonewton per linear meter. The dead load excludes the beam weight. Ang beam weight, yun yung minumultiply natin yung dimension by the unit weight of concrete na 23.56 or minsan 24. O kaya, kung kaya mo ng unit weight ng concrete, alam nyo to sa physics, di ba? Yung relative density ng concrete will be multiplied by the unit weight of water para maging unit weight ng concrete. So kung ano man, basta excludes ang beam weight. Yung concentrated load daw ang midspan ay live load. So ito yung strengths. O ano yung problema? Ito, wala namang problema. Challenge. So itong articulation number 4, we are challenged to determine if this is adequate. Ayun na yan. I-compare natin. Siyempre, by the virtue of what we learned in the strength of deformable bodies, simply supported pa ito. Simply supported. So, i-support niya lang ng ganito, may dead load, may live load. So, ibig sabihin, may factor tayo na ganito. Pero ito muna yung set.
May malapit.
So, if this is 500, the given is 437.5 as effective depth. Well, we know this already. The equivalent is equivalent rectangular stress block. And then, in our country, we have this type of bar size accordingly. Numbered as 3, 4, 5, 6, 8, 9, 10. Walang 7, no? So, ito 10 millimeter, number 4, ganyan. Ganyan yung ano niya. Tapos ito yung manual. Ang sabi, for number 8. So, kung number 8, hanapin mo yung number 8, apat daw nung. Apat na 25 millimeter diameter. So, yan pala yung given. Apat na 25 millimeter diameter. Compute muna natin yung minimum steel reinforcement. You know this already. You don't have to memorize it. By virtue of practicing it, unwittingly, you can memorize it. And this will be 0.25 FC prime over Fy. BWD must be greater than equal to 1.4 BD over Fy. Pagkatapos nun, mako-compute na natin yan as 416.38 square millimeters. Remember, it must be greater than equal to So, yun yung threshold natin. No? So, yung 4 ay dapat less than, di ba? 1 point, which is good. Oh, less. Ito. Mababa rito. So, mas malaki. Tama naman. Okay? Okay, good. So, punta tayo sa design strength. So, yung A can be computed based on the AS, FY, FC prime, and D. And then we can compute for the Z. And then we can then compute for the actual magnitude of it. And then the nominal moment is AS FYZ, which is equal to 308.7 kilonewton meter. Pwede natin gamitin yung, by the way, may safety factors na to na 0.1, no? Kaya 0.9 ang multiplier. Naging 277.83. Ito yung design strength. We can also solve this magnitude by virtue of coefficient of resistance. So may steel ratio ka, which is 0.01496. Kinumpute ko na yan. Recomputed, paki-recompute nyo na lang. At we have omega, just like what we have presented in the previous slide. Rho, steel ratio Fy over Fc prime, ako-compute din yan. And then the coefficient resistance. Fc prime omega times 1 minus 0.59 omega. And then we equate this, we can compute that as 5.3734. Remember the formula? RB squared. So phi b squared bar b squared and 0.9. This is equal to 277.7. Parehas na rin, may konting differential lang. Pero kung ayaw mong gamitin ito, gamitin mo to as the maximum. Pwede naman. Design capacity. What is the required strength or the service moment? Yun yung tawag natin sa WSD. Diba? Meron tayong beam weight. Beam weight natin. Yun yung dimension multiplied by relative density multiplied by the unit weight of water. Meron tayong 11.7. Sabi rin,
Hindi na taas yung wood. Paano eh?
we also have superimposed concentrated. That is live load accordingly. And that will be multiplied to 1.6. But this is concentrated load, which is equal to 69.44 kilonewton per linear meter. So apparently we have two distinct types of loadings for the simply supported, which is uniformly distributed, which can be computed as WS squared over E, and a concentrated load at midspan, which is PUL over 4. If you can then, and this MU as the service moment can be compared now to the MU of the design strength. Okay, syempre, dapat mas malaki ito kesa dito.
Walang laki.
So, yan yung sinasabi natin.
Tumatakbo na lang ako.
Ibig sabihin, the beam is adequate. Kasi pag ito mas malaki doon, di inadequate. Pero hindi naman pinapadesign. Pagka nangyari yung mas malaki, you need to revisit the dimension. You need to revisit the AS. Kaso hindi naman, kung halimbawa nagkataon mas maliitin, no? Sasabihin mo lang inadequate, hindi naman pinaparedesign. Ito yung gagawin natin. Alam niyo na. You know what to do. Yeah.
Buksan mo yung payo.
Please be back in this link. Alam niya na. Balik lang tayo.
Recording stop.
Makakadaan mo yung eco bike? Hindi makakadaan yung eco bike? Fuck!
Recording in progress.
Wala.
Recording in progress.
Okay, papadala ko na lang. 131, whole body. May tanong ba?
Po sa isa po naming subject which is construction methodology, nasa estimating na po kami. Tapos po, syempre po di ba pag nag-estimate, need po natin kunin yung design ng beam para po makuha yung mga stirrups, ganun po ako ilang bakal. Tapos sir, ano po, kapag po, di ba, syempre pag mag-design po tayo, wala pa naman po tayong specific na beam.
Mabilisan talaga.
Po.
Mabilisan talaga yung salita. Pag mabilisan tayo, wala.
Di ba po wala po naman po tayong specific na B and D po na yung length and naka-indicate na kung ano po yung appropriate na length and width ng beam or kami po yung bahala mag-design.
Well, sa ngayon, ano ang alam mo na WSP, di ba? So, pwede design WSD ay malaki kumpara sa dimension mo ng design sa USD. So, hindi ko pa nasasagot yung tanong mo. Dahil may alam ka na sa design ng WSD, pwede mo sagutin yung, kung ayaw mo itanong sa akin, pwede mo sagutin na mayroon ka ng design. I-design mo nga lang ng by WSD. Ngayon, dahil naintindihan, kung hindi pa ganong naintindihan ng USD, you will stick to the WSD. Pero bibigyan na kita ng notice at para sa iba rin na yung design dimension ng WSD usually mababa ng 20% sa WSD, yung USD mo. So, ibig sabihin, mas maliit, mas compacted. Mabe-verify mo naman yan. Hindi parating gano'n. Titingnan mo lang. Usually lang, pag mabe-verify mo yung mga 10 to 20%, parang gano'n. Nakikita mo. So, kung wala pa kayong design, i-design mo muna yung Giga by WSD para sigurado na meron ka mako-compute, di ba? Hindi ko naman pwede.
Sir, kami po din yung parang mag-i-indicate kung gaano siya kahaba and yung length and width ng beam po. Kami rin po yung
Okay, ganito yan. Yan. Magandang tanong yan. Ang tawag dyan, framing. Structural framing. Siyempre, kailangan natin may architectural plan muna. Yung architectural plan, dun mo ibabase yung structural framing mo. Saan mo ilalagay yung poste strategically, saan mo ilalagay yung biga. Halimbawa, ang pinag-uusapan natin ay 5 meters by 5 meters. So, ibig sabihin, kung 5 meters by 5 meters, as a structural engineer, it is your call whether you want to place 4 columns. Saan mo ilalagay yung 4 columns? At the corners. 5 meters, 5 meters. And then you design it. Yung biga mo, ang length 5 meters. Nakuha? Pwede rin, as a designer, pwede mong gawin yung column mo, medyo magastos nga lang, stick to 2.5. So, 2.5 yung distansya ng column, ibig sabihin, 2.5 yung length ng beam. Pero hindi simply supported yun. May column ka sa gitna eh. So, continuous beams yun. Ang atake doon, ang analysis doon, continuous beams. So, hindi mo naman, pwede ka naman hindi mag-dwell sa computation whether free moment or moment distribution. Meron tayong mga coefficient na ginagamit. Kapag two spans, may mga gana, balik lang kayo doon. Kung WL squared over 16, WL squared, mga ganon eh. Balikan mo yun, yung mga ganon. Pwede mong gamitin yun as working moment. And then you design it. Kaya, tapusin ko lang sa sagot na to, Miss Gladys, mahalaga yung algorithm sa Excel sa ngayon. Wala ka pang app. Napansin mo, i-enter mo lang yung mga binabagong yung mga nagbabagong values, di ba? And kung may algorithm ka na sa Excel, titignan mo na lang yung dimension. Tama ba? Yung kahalaga. Kasi naka-imputed na yung formula. So, mga analyze na yun. Yung estimate mo. Kaya lang pag nag-estimate ka, sa bakal pa lang ba kayo o sa konkreto?
Mag-i-start pa lang po kami sa next lesson po namin. Mag-i-start na daw po kami ng estimate. So, natanong ko lang po kasi nabigyan po ako ng parang hint ng mommy ko po kasi engineer din po si mommy. Nabigyan niya na po ng hint sa estimate po.
Oo, tama lang yung hint. Kesa naman yung siya yung magsasabi. Tama yan.
Tinatry ko nga po magpaturo tapos sabi niya, paano ka matututo kung ako yung
Oo, tama yan, Tol. So, ganito, Tol, no? Ay, Tol. Guys, Daddy. Yung sinasabi natin na estimate, dyan napapasok, everyone, yung bend. Ilan nga uli yung squala natin? Kasi sa site, ang tawag namin squala eh. Ilan yung bend uli, mga utol? Yung, di ba, meron tayong biga. Ayan.
L over 4.
Yung bend ng bakal, kunwari sa anchorage. Ilan yung dawa, 16 mm. Ilalagay mo sa kabilang poste. I-anchor mo. Ilan yung bend nun? Yung squala. 12 dB. 12 times the diameter of the device. Naalala nyo? And then may embedment length na 40 dB. Balikan nyo lang yun. Balikan nyo. Sa ngayon, hindi masyadong memorize. Kaya, hindi ko kabisado yan. Parati ko lang ginagawa. Kaya, unwittingly, na-memorize ko. So, parati mong ginagawa, yung formula, na-memorize mo. Pero pag nakalagay sa Excel, as much as possible, kinocompute ko pa rin ang calculator. So that you will be guided with the governing principle. Yung formula, hindi mo makakalimutan. Kasi otherwise, you will be independent with the Excel. Na wala ng kuryente, na lobat, hindi mo na alam computein yung maximum mo. Okay? Thank you, Daddy. Pag pag nag-estimate kayo, pwede na kayo sa trade ng pag-estimate. Ayos na yun. Maganda pumunta kayo sa mga napakaswerte nyo nga eh. Mag-click lang kayo ng, halimbawa, 3-story residential house. At in a span of seconds, meron na kayong picture sa Google ng 3-story residential house. At meron ka pang architectural plan. O lagyan mo ng structural framing yun. Pag sinabi ko structural framing, lagyan mo muna ng, syempre, ng footing, poste, taspiga. Pero darating din tayo dyan. Ang sinasabi ko lang, kami. Pag sinabing, you look for architectural plan, pupunta pa kami ng DPWH, pupunta pa kami ng City Hall, wala kasi ganong tipo ng resources na meron kayong ngayon. Di ba ang ganda? Ang gagawin mo na lang, mag-aaral. Ang gagawin mo na lang, maghahanap, itatype ng kung ano, kami pupunta pa talaga. At babayaran mo ba yun? Hindi libre yun. At kung tamad yung hahanap ng plano, ikaw pa ang hahanap sa bodega nila, sa port area, sa DPWH. Kinukwento ko lang sa inyo kung gaano ka-bless yung sitwasyon niyo bilang isang mag-aaral. So, nasa sa minsan kasi may drawback eh. Pag nakahain na lahat, yung kutsara, yung tinidor, yung plato, yung tubig, nasa harap na, minsan, kailangan pa may magsugo. Diba? Yun yung drawback eh. Nasa sa atin ngayon. Tayo na yung, wala nang ibang magbabago nung kundi tayo na. Pero meron naman, out of reach, ang layo ng pagkain, pero they decide to have that nourishment. Pinipilit nilang makuha yun. Matanda at mature na kayo para maintindihan nyo yung metaphor ko. So, pag hindi nyo naintindihan, balik tayo sa meta 3. Joke yun. Ano ba? May iba pa ba?
Sir?
Wala na. Mukhang,
Sir,
sige.
Sir, yung sa SEU 6 po ba, sir, meron na pong ano?
Ano?
Yung kailan po, sir, ang deadline po? SEU 6?
Yeah. Okay, men. Sino ba yung nagtatanong?
Ilikay po, sir.
Ilikay.
S po, sir.
Ano sa tingin mo maiintindihan mo yung SKU number 6?
Ano po yun, sir? Medyo...
Ilang araw mo maiintindihan sa tingin mo? Kung bibigyan mo ng pansin.
Hindi ko ba po sure, sir. Kailan niya po ba bibigay?
Hindi. Sabihin mo nga sa akin. Next term, next 2 weeks, next 3 weeks, ano?
Kayo po, sir.
Ako?
Flexible naman po kami.
Basta wag mo lang ipasa ng after ng module 1.
Pero sir, hindi niya pa po ata nabibigay sa amin, sir. Kasi wala po tayong klase nakaraan.
Ganun ba?
Opo.
Kasi may kasakit ako eh.
Ganun po ba?
At saka nasabay ng, ewan ko, nagdadahilan lang yata itong conference.
Pagaling po kayo, sir.
Hindi, magaling na ako. Ano lang, yung sa, siguro, kasi pagka wala akong klase, concert ako, kaya, ano ba? Ilikay, solve mo lang muna. Hindi ko na kayo ipe-pressure kung kailangan nyo ipasa. Mahalaga maintindihan nyo. So, para kasi yung susunod na activity nyo, bibigyan ko kayo ng isang structural frame. So, solve nyo ito ng by WST. I mean, i-design nyo to by WST. I-design nyo to by USD. Para makumpara nyo. So, ganun yan. At sa pag-design na yun, kailangan alam natin yung mga konsepto na yun. Babalikan lang, wala naman kailangan i-memorize. Sabi ko nga, unwittingly mo.
Higilid ko man, pamerapan sa atin. Masikip eh.
Ilikay na sagot ko ba?
Yes po, sir. Thank you po.
Mas thank you sa'yo. Ano pa? Mukhang wala na.
Thank you po, sir.
Mas thank you sa inyo. Lahat yan, gawin natin yung SBU number 6. Try muna natin. Huwag niyong isipin. Maalala lang naman. Alam ko, alam niyo na, no? huwag niyo isipin na kapag binigyan kayo ng task, ay papagurin kayo. Pag binigyan kayo ng task, anong tawag nito, pinagtitripan kayo. Isipin ninyo, itong task ito ay para mas strengthen yung understanding natin. Ganun talaga eh. Dahil wala tayong magagawa kundi mag-practice. Salamat, mapupuno yan parate, pero tandaan natin, iba pa rin if we remain humble. Be blessed, be safe. Maraming salamat. Bye.
Thank you po, sir.
Thank you po, sir.
Thank you, sir.